All right. So now on to the first question. So in this question it says gravitational field strength for just 1 mark, okay? You're just gonna write that it is the force of attraction per unit mass, and that's all you need to do. Okay. Now, speaking of this, then we have the next question is about, it says that the figure 1.1 sketch a graph to show the variation of gravitational field strength of star with distance from its center. You should consider distances in range R to 4R. So at R, obviously the field strength is going to be the maximum. That is this point. And then you guys should remember that the gravitational field strength is proportional to 1 upon R squared. So when you put 2R and square it off, then basically you get a quarter. So of R square, right? So a quarter would be um 0.25, which I believe is going to be somewhere here. So at 2R, it's going to be here. Now, then I need to use the calculator. That's not good. So 1 upon 9 for the next one, because 1 upon like 3 square and 0.1, right? 0.1 will be somewhere here. Oh my God. Wait a second, please. Okay. Okay, so it's going to be somewhere here. And then for 4, it will be 1 upon 16 because 4 square is 16. And 1 upon 16 is going to be 0.625, which is somewhere here. And then what you're going to do is just draw a smooth line like this, like that. So that would be the graph of gravitational field strength, which is very similar. So basically what they want is they want to draw the red line from this graph, actually. All right, with values. So you should just be careful about that. If you have any questions, please let me know here.
Sir, like where did you get the values from?
I didn't get I know that at the surface, because it says the gravitational field strength at the surface is GS. So which means that at surface it should be this. And then what I'm doing is I'm just putting um, at 2R, the gravitational field strength will be like 2R whole square, right? So it means that now it will be a quarter of R square. So I'm just I'm trying to find the value. Like I've found the value at a quarter. So 1 quarter is 0.25. So I got it here. Do you understand? Then for 3R, it is going to be like this. G is proportional to 1 upon 3R whole square. So I get G is proportional to 1 upon 9R, 1 upon R square. Do you understand? Like this?
So you're like doing 3 square and then you're getting 9R squared.
Yeah. So 1 upon 9 would be 1.1. So I got, this is 0.1 on the graph. So just above it, I got it here. Understood? And
Oh,
then
okay.
when I do 1 upon 4 R whole square, then I get basically 1 upon 16 R square. So 1
16.
upon 16 is 0.625. So I got it here. That's why this is the point. Do you understand?
Yes, sir.
So the idea behind this graph is that if you look at the graph, I never touch the x-axis because it will never touch the axis anyway. Because you can keep on, adding the values and it will keep on, reducing, but then it can never touch the zero line because it goes till infinity, right? So make sure it does not touch x-axis. All right, never. So that is something you should remember. Now, in the next question, it says the Earth and Moon may be considered to be spheres that are isolated in space with their masses concentrated at the centers. The masses of Earth and the Moon are 6, and this is the Moon, this is the Earth's mass, and radius between them are 60 RE. Now, what exactly is RE? RE is the radius of Earth, so that's in terms of this, right? Now, in this particular question, it says that you got to find the you got to explain why there is a point between Earth and the Moon at which the gravitational field strength is zero. Now, what you guys need to remember that at certain point in the middle, there is going to be a null point. Now, there are certain properties of null points that you need to remember and just add it in here so you can remember it. So at null point, the net force is equal to zero. You should always remember that. Okay. Then if you go to yeah. And then obviously the next thing you should remember is that the net gravitational field strength is also zero. The reason is that obviously the moon will try to attract the mass in this direction. So force of moon is in this direction, and the equal force of Earth is in this direction. When you add the forces, obviously it's going to give you a zero value, so it's balanced here. And then obviously the gravitational field strength of moon and the gravitational field strength of Earth are in opposite direction. They're vector quantities, both are vectors. So when you add them, obviously the net gravitational field strength is also zero. Understood?
Yes, sir.
Then the third thing you should remember is that the at this point, the net gravitational potential potential is maximum. Now, this point, we're going to talk about this in a later question, but right now you can just, remember that these are the 3 points that define a null point. All right, so this is basically properties of a null point. All right, nobody's going to ask you this. It's just like in these type of questions, they're going to ask you what is happening. So explain why there is a point between Earth. So you're going to say that the attraction, like all right, so you're going to say that the force, or you can write gravitational field strength, at this point are equal and opposite. Hence, the net, if you've written force or gravitational field, so whatever you've written, is zero. Is that clear?
So the 2 marks are for equal and opposite.
Yeah, obviously. So
Okay.
you need to define. If you do not write opposite, you can say these are like vector quantities. Okay. So if even if you say it's vector quantity, that is also fine. Okay.
Okay.
Yeah. So yeah. So you should always do that. The opposite has a sign. Obviously, the resultant has a sign. Net writing net or resultant would be carrying a mark. Okay. Just remember that. Anyway. Now, then it says determine the distance in terms of RE from the center of Earth at which the gravitational field strength is zero. Now, considering this factor, we already know that the forces or the gravitational field strength are equal and opposite. So I can say at this point, at null point, the gravitational field strength of Earth is equal to gravitational field strength of Moon. So I'm going to write Gm of Earth over radius of Earth whole squared, right? Equals to Gm of Moon divided by radius of Moon whole squared. Do you guys agree?
Yes, sir.
Of
Okay,
course,
now
yes.
The thing is that now, obviously, if G and G is the constant, so it just cancels out. And now I need to see what we have. The interesting thing about this question is that the distance of between Earth center and the Moon center is given, but at the null point, no distances are given. So I can just, write it in terms of something. Like, for example, I could say, if this distance, in fact, let's write this as let's write this R. Okay, let me just write R because this is confusing because they've already given RE in a different manner. Anyway, so I could say if this distance is R from Earth, so then this distance, can I say it is 60 RE minus R? What do you guys say?
Yeah, it's correct.
Right? So then
Yeah.
I could say that from this, I can write mass of Earth divided by R squared equals to mass of Moon divided by 60 RE minus R, and that should be my equation right here. Okay. Now, the idea is that now we have certain values already given, like mass of Earth is 6 and that. So let's put it there. So it's going to be 6 into 10 raised to power 24 divided by the radius is r squared equals to 7.4 times 10 raised to power 22 divided by 60. The radius of Earth, we need to find, I think, what do we need to find really? In Okay, in terms of RE, we need to find this. Okay, wait a second. If this is 60 RE, then obviously that is going to be, yeah. Okay. So then what I can say is I can say, all right, this is going to be 60 RE minus R whole squared. Now, whenever you have like a function like this, right? So there's a tip here, and the tip is that always take root. When you take the root, basically it makes it less complex, which I mean, what I mean by this is that if you take the root, it will be 6 into 10 raised to power 24 under root, and this will just cancel R. And why this is important? Because otherwise you'll get a quadratic equation, and we don't want that in our um, solution because then it will take too long to basically solve this. All right, is that clear?
All right.
Sir,
Now,
like first of all, I have a question is that like from the 60 RE, how did you find how long is R?
I just assumed. Now, let me just draw it like here. Okay, again. I just
No, because
assumed.
like even the to find the null point, you have to like do some kind of work, right? So
No, what I'm doing is I said this is the null point. Let's suppose. I'm supposing this is a null point, right? So
okay,
from the center of Earth to this null point, can I just assume that this distance is r?
yes,
Okay. If I assume this is r, then from the moon till null point, can I say the distance is 60 RE minus r? That's the
yes,
remaining, right? So I'm putting it right into, because this is equal to the radius of the distance from the moon, and this is equal to distance from the earth, like this. Okay. So I
okay,
put it right here and here, you see.
okay,
And now what I need is he's saying find this r. Oh my god. Find this r that you see in terms of RE. So I got to find this. So I have to find this. I have to make this the subject in terms of RE. Do you understand?
like how
That
much RE is it?
yes. How much RE is R? Do you understand?
Okay,
Like that.
okay,
So then basically to if I had not rooted this value, then it would create a quadratic equation. I don't want a quadratic equation because then it would cause a lot of problems. It will take too long for me to solve. Understood? So I took under root to remove that. And now what I can do is I can simply write this as 6 into 10 raised to 24 divided by 7.4 into 10 raised to 22 under root. And on that side, it is r over 60 re minus r. Now I can just use my calculator to quickly solve this. You do this, you do this. It's very, it's a advice that if you do not have the natural display calculator, you should buy one because it will help you make less mistakes in the exam. So this is going to be 9, right? This is 9. And this is going to be 9. And then 60 RE minus R equals to R. So 60 into 9 is 540 RE and minus 9R equals to R. Can I just write it as 540 RE equals to 10R? And then when I divide this will be 54 RE. Do you understand? So R will be 54 RE, and that's what he's asking for. Understood?
Yes.
Sir, I have a question.
Yes, please, Javeria.
It's not from the second part. For the first part of the question, explain why there's a point. Could they, for example, give us two humans and then ask the same question? Explain why there's a point between human 1 and human 2 at which the gravitational field strength is 0, or am I saying a very wrong point? Could they do that?
Well, they could definitely do that, but
Oh,
they will
okay.
not do it in the exam. Because
Oh,
what you need to understand is that the Newton law of gravitation um, is really significant when the masses, one or the both masses are very large. Do you understand? The
okay.
reason why you cannot attract your phone visibly, like you are, but the force is so small that it hardly is significant.
Hardly
Do you
matters.
understand?
Okay, it hardly matters. Okay, okay.
Yeah. So they will never give you a question like this, but obviously there is a force and there is a null point between two masses always. That's true. Okay.
All right.
Do
All
you
right.
get my
Thank
point?
you.
All
Yes,
right.
I do. Yes.
Now, so then, if you look at it and with no questions, please let me know so I can go forward then. All right. Now, uh, do not worry about the space because although this is from the actual paper, but because I've cut the questions from the paper and put it here, so obviously the scale of the whole thing will be larger in the actual exam. So don't worry, there will be space. Then going to this important. Now, whenever you are going to make a graph of net gravitational field strength, because in this one, and it will always be like this. It will always be like this in the exam. The moment you see surface of Earth, surface of Moon, or any other, planets or stars or whatever, you should understand this is a net gravitational field strength graph. Now it says on axis sketch a graph to show variation. So first of all, I'm going to show you how the gravitational fields from each individual mass changes, and then we're going to make a net graph, and I'll tell you which graph will be, in the exam that you need to draw. So considering the fact that the gravitational field strength on Earth is 9.81 newtons per kilogram. And if I correctly remember, for Moon, it is just 1.67 newtons per kg. And now, why I have put it in the negative direction? Because obviously, if the Earth is this and the gravitational field strength of Earth is pointing towards this direction, right? So I can say if this is positive, then obviously the moon's gravitational field strength is in the opposite direction. So I have to take it negative, or you can do vice versa as well. Do you guys understand this?
Yes. Yeah.
Now, so what you're going to do is you're going to put a point here and just put a point on the moon like this. Then draw straight lines. I have explained it to you in the previous lecture as well. Why from the center of Earth to the surface of Earth. What the? Wait a second, please. I don't know what is happening here. this app is going crazy. So first of all, oh my goodness, wait a second. This is making me so angry. Okay, so here, what? Let me restart this app. Sorry, this is going crazy. So the other Ahmed is not here. Where is he? Where is he, Munib? You should know about your friend.
Oh no, sir, he's probably busy.
Okay. So now you draw a straight line, and then the line would be like an exponential decrease like this. So this is how it should not touch the x-axis, by the way. This is how the gravitational field strength of Earth is going to change. I should have made it in just one line like this. Let me remove this. Okay. And for the moon, what you're going to do is you're going to make a straight line like this, and then you're going to do the same thing for the moon. Okay. It should be exponentially decreasing, not like that, like this. Okay. Now, so this graph is for Earth, as you can see, and this is for the moon. But in the exam, these two are not required unless they say, okay, draw, the graphs of this. So what you're going to do is you're going to draw the net graph, you're going to start from this point, like you draw this line, you're going to start from this point, and then you're going to drop the line such a way like this, and then cross it where it seems both graphs seems equal, right? Because that's where the null point is going to be. And then cover it with moon like this, like that. Let me just draw moon above, a bit above it. All right, like this. So actually, in reality, what you need is you just need um, the blue line, this net graph, right? And that's what they're looking for. That there should be a clear, crossing here, crossing at the null point. Is that clear, everyone? So what you should be expecting is you should be expecting a graph like this only. Understood?
Yes, sir.
Yeah, no need to draw the other two lines. This is just for you that I wanted to explain how it crosses there, because that shows the null point. And if they give you the graph, that is also an indicator that where it crosses or touches the x-axis, that's the null point with the net gravitational field strength is 0. Anyway,
Sir, could we make any point the null point? Does it have to be that far and that close to the surface of the moon point, or could we make it in the middle?
no, you cannot do that. Obviously, the field strength of moon is very smaller, right? It's very small. So where Earth and moon will meet will be closer to the moon, because as you go away from Earth, its gravitational field strength is reducing. And as you go closer to Earth, the gravitational field strength is increasing. So the mass that is smaller will have the null point closer to it. Understood?
All right, thank you.
So we can assume the null point anywhere closer to the surface of the moon.
Yes, yes, it must be closer to surface moon.
So the graph could be the opposite to right. I mean, the Earth down and the moon up.
Like, yeah, even if you want to draw it a mirror image, it would not change the fact. It would be like this. It's still the same.
Okay.
Understood? Then you just need to write that, okay, this is the gravitational field strength of Earth, and that's the gravitational field strength of Moon. Just need to, flip the signs, everything else. The magnitude doesn't change of the point.
So
Understood?
by the two quadrants, we're trying to show that the field strength is opposite, right?
Yes, because the field strength is a vector quantity, and obviously the traction is happening in opposite directions. That's why.
Okay.
Okay. All right. I hope you guys understand this. And now we're going to go towards the graph of gravitational potential at a point. Now, gravitational potential graph is basically what they're going to give you is it's pretty simple. You don't need to do anything else. One thing that you should always remember when you're drawing this graph is that gravitational gravitational potential is never positive. And we learned it through the definition and this part where I told you that you could either go to zero gravitational potential, which is at infinity, and before infinity, every value is zero. All right. So if you're moving towards infinity, obviously you will have a increase in gravitational potential, which means the gravitational potential becomes less negative. And if you're going towards the mass away from infinity, which means that the gravitational potential is getting increasingly negative. So you're only talking about in terms of negative. It can never be positive. So if it can never be positive, then we should understand that the graph will also have just one axis, right? So it looks like this, and the gravitational potential sign is here, and we're right now taking as megajoules per kg. So for example, for Earth, we should remember, I mean, you should not remember this, but it's fine if you do, that the Earth gravitational potential surface is 62.7 megajoules. And suppose this is the radius of Earth at this point, and we're looking at 4r, like it could be like 1 or 2r, 3r, whatever. So I have a value like at 4r distance from Earth, the gravitational potential increases to 15 minus 15.7 megajoules. So the gravitational potential would be like at this point, it would be like this. And now the graph at 4r will be here. So it basically is a curve like this, and it keeps on going like this. So you need to decrease by, as gravitational potential is proportional to 1 upon r, right? So as you go away, it just makes a less sharp curve like this, okay? And what you guys need to remember is that these sort of questions, usually they would ask you to either draw the graph between r and some other r, or they would ask you to get values from this. All right, we are going to look at that in just a bit. So you can just copy this right on your PDF, and then we're going to go forward. Interesting. Okay, done.
Yes, sir.
Okay, now let's go and check this question out. So first of all, again, we're asked to define gravitational field strength.
So could you go back for a second, please?
Okay, sure. I'm sorry. You can copy this.
No, it's fine. So where did you get the values of 15.7 and stuff?
You don't need to remember this. I remember these. That's why. They're
Oh,
actual
okay.
values. Okay, so I just wanted to make a statement here. Okay, that gravitational potential becomes less negative as you're moving towards infinity, right? So this is going towards infinity. Understood? And if you
Okay.
go closer to any mass, then obviously it's going to decrease
It
further.
becomes less negative as you move away from infinity.
Yeah. And the maximum it can go is still zero. Okay.
Okay.
So if you move in this direction, it is getting more negative. If you move in this direction, it's getting less negative. It can never be positive. That's why we have to write it like this. Okay.
Okay, sir. Thank you.
Okay. So then it says define gravitational potential at a point. Like, we should remember the 2 points. First point is that it is work done uh, per unit mass. Okay. And then 2 in moving this mass from infinity to the point. You can add within the field, but that doesn't matter if you want to. But this is the required statement that you need to put. Anyway, now this graph is the classic gravitational potential graph. Now, the reason I wrote megajoules here was because in most of the question, they're going to give you this. All right. So if you see this, so I just want you to always check the units and prefix, because sometimes we forget, obviously we humans, and we ignore that, okay, and we take the direct values that would give you a wrong answer. So you should always check that it's -7. Anyway, now it says the radius for Earth is this. By considering the gravitational potential at the Earth's surface, determine value of mass of Earth. Now, I just want to tell you something very important here, right? The mass of Earth is 6.0 times 10 raised to power 4 kg. This is a universally accepted value. Now, let's suppose if I'm a student, I just remember this, right? By doing so many questions. And now I should remember, okay, if I'm doing this question, my answer to this question should be close to this, because Cambridge will never give you any question that is not close to the accepted value that's universally, right? Let's suppose if my answer is coming as 2 into 10 raised to power 24, then I should understand that I have done something wrong, okay? So remembering these kind of things help you not make a mistake. Anyway, so at the surface of Earth, this is the radius. I'm going to go down and I'm going to go this point. And as you can see, it is almost in the middle right here. Okay. So then I'm going to say this point is, how do I check this? If I do not know that, okay, this is 6 and 8, I'm going to subtract them. 8 minus 6 is basically 2, and 2 divided by how many boxes are 10. So each point represents 0.2. So this is basically 6.2. This is 6.4. So this would be 6.3. Everybody agrees? Okay. So the value is minus 6.3 times 10 raised to power 7 joules per kg. This is basically the potential that I have at the radius. The radius is given as this, and I know that the formula for gravitational potential is minus gm over r. That's it. So I'm going to put minus 6.3 times 10 raised to power 7. G value is 6.67 times 10 raised to 11. I know this, but you can, if you don't remember, that's fine. You can look at the data sheet at the end of the first pages. And the radius is given as 6.4 times 10 raised to 6. Again, check, sometimes they give you in kilometers, so you should be aware of that. Minus will cancel out, so it hardly matters. And then 6.3 times 10 raised to power 7 multiplied by 6.4 times 10 raised to power 6. And then you just need to divide it by 6.67 times 10 raised to power minus 11. Minus 11. Okay. So as you can see, my answer is basically 6.04 times 10 raised to power 24. Now, how am I sure that my answer is correct? I'm sure because I know that the universally accepted value is this. Do you guys understand this?
Sir, where
So
did you get
this
minus
is,
6.3 into 10 to the power of 7?
I got it from graph, Mokshit, like here. You see? So I just checked that what will be the potential value at the radius. Radius means that this is how the Earth would look. Oh, do you understand? So this is the radius of Earth. So at the surface, it would be this value that I've checked, this value. Do you understand?
Yes, sir.
So you have to do it with the graph. Have I answered your question? Is it clear?
Yes, sir.
Okay. So this way I get 3 marks pretty easy, not a big deal. And then in part 2, it says, okay, it says a meteorite is at rest at infinity, and the meteorite travels from infinity towards Earth. The calculate the speed of meteorite when the distance is at 2r above the surface of Earth. Now, this is a very misleading statement because they're saying 2r above Earth's surface. It means that actually they're talking about 3r, not 2r. Do you guys understand this? Because 2r above would be 3r, right? So basically, they want you to make this mistake that you should take 2r, but you're not supposed to take that. You need to take the potential at 3r. Understood?
Yes.
Okay.
Sir, like
Now,
why are we taking 3R?
because if you read the statement very carefully, it says calculate the speed of meteorite when it is at a distance 2r above the Earth's surface. Earth's surface is at r. So 2r would be r plus 2r means 3r, not 2r. Do you understand?
Okay. So like first time you read it's okay. Yes, sir, I understood.
So basically, like this is, they are like testing whether you read the question carefully or not. Okay. All right. So whether you hate the examiner for this or not, but you should be aware of this, that they are going to play this trick on you a lot of times. So you go at 3R and now you check the reading here. So this is basically 2.2, like at this point. So you can see this is 2.2. So the point I have will be minus 2.1 times 10 raised to our 7. Agreed?
Yes,
Okay.
sir.
Now, so what is happening? The gravitational potential energy will change into the kinetic energy because it's coming from infinity to this. So you're losing potential. Now, you need to understand that the potential, gravitational potential energy can be found out by, because gravitational potential is work done per unit mass. So it means that work done is potential times mass. So I'm going to write gravitational potential times mass equals to half mv square, right? Now, the mass of the meteorite is irrelevant. It gets cancelled out. The potential we found out was basically 2.1 times 10 raised to power 7 um, joules per kg and half, and we need to find the speed. Okay. Notice that this time the answer that I got was basically here I had minus sign, but I completely ignored minus here. Do you guys know why? Now, remember, when you're comparing something, from infinity to that point, you should remember what you're doing is you're actually finding the change in potential from infinity to 3r, right? At infinity, the potential is 0. How do you find change? Minus 2.1 times 10 raised to 7. That's why it is positive. Do you guys understand this? So just this is just something. Just remember that it's gravitational potential energy. Obviously, you're finding anyway. We go to, let's do it quickly. 2.1 times 10 raised to power 7, and
Sir,
then
the
you
screen's
multiply
lagging.
2, and then you, so it's 6 10 raised to power 7.
Sir, your
Actually,
voice
is
was
lagging.
like yes, sir.
Sir, the screen and your voice lagged.
Okay, wait a second. Wait a sorry. Let me put it like on a different internet. I don't know. This doesn't have.
When says asking questions, why don't you all answer?
Hello.
Yes, sir, we can hear you now.
Okay. Can you also see the screen?
Yes, sir.
Good. Okay. So, what I was talking about was that basically you guys need to remember that it's like, all right. So this would be the answer. If you have any questions with this, please let me know. Everybody. Okay. So,
Like
Anush,
you were explaining something, you removed your negative sign. Why is it?
I removed the negative sign because you see, we are dealing with like the mass. Suppose this is the point at infinity, right? And this is the point at 3r. So it's moving from infinity to 3r. Do you agree? So at infinity, the potential is 0. At 3r, the potential is minus 2.1 times 10 raised to the 7, right? So when you find change in potential, you do potential in infinity minus 2.1 times 10 raised to the 7. So obviously it is going to be positive like that. That's why.
Wow, okay.
Okay, so we get this answer. Fahar, do you understand? And where is Falak? Okay, Falak, I don't know, maybe. Gatika, do you understand? Muneeb, Sumant, Ahmed?
So why did you take the work done equation?
Because I have the potential and I have the mass. So that's why. That's why, Gatika.
But why didn't we equate it to kinetic energy?
Because when you go, let me just talk about this, okay? This is Earth. If you throw a stone away from Earth, what do you say? Gravitational potential increases or decreases?
Increases.
Why does it increase? Because you're throwing the stone towards infinity. Do you understand?
Yes, sir.
And when it is falling back, what do you say? The gravitational potential is changing to,
It's decreasing, more negative.
but it's changing to what?
Kinetic energy.
Kinetic energy. That's why I've taken it. Do you
Oh,
understand?
okay.
Okay. Now, so then it says in practice, Earth is not an isolated sphere because it is orbited by Moon as illustrated, and this is the initial path. It says suggest two changes to the motion of meteorite caused by the Moon. Okay, who's gonna tell me? This is pretty easy. Will the meteorite also get attracted to Moon or not? Right now, look at the Moon.
Yes.
So
Sir,
then,
I think the
yeah,
gravitational field strength for Earth is more,
yeah,
is
but
it?
it is true. But will it be affected by Moon or not? That's my question. That's
Like
their
if we compare the gravitational field strength of the moon and the earth, and if we get to know like the earth is more, so obviously it will be pulling the meteor towards the earth, right? So I am supposing it will deflect towards the earth.
even if that's absolutely correct. What I'm saying is that if the meteoroid is being affected by Earth in this direction, so this is the fourth of Earth, even if the moon force is very small, wouldn't it cause the meteoroid to have a resultant force somewhere in the middle of them? What do you say?
It will, but I feel like even the resultant will be to a bit towards the earth, right? Since the field, the force from moon is less.
Okay, so can we say then it will still slightly bend away from the path that we are assuming it to have?
It
That's what
should
I'm
be a
saying. It will
deviation.
bend.
There will be a deviation.
It will.
It should be a deviation, right? Because the moon
Yeah,
is still there.
yeah, moon is still there. So even if the force is small, but there still be a little bit deviation, don't you think so? Maybe in small degrees.
Yes, so there will be a little deviation
Okay.
towards the moon, but I feel like most of it will be towards the Earth, right?
Yeah, that's true. That's true. But we are considering what will happen. What is the effect of moon? So we will say it will deviate, all right, from its straight path if it's just moving towards Earth, right? And the other thing is, if you see where the Earth is and where the moon is, and the force is not against the force of Earth, don't you think the force will have an added effect to the acceleration of it? That's my question. If there is a small boat being pulled by a very large boat and then pulled by a very small boat again, don't you think that its force and its force will cause a greater acceleration if if considered that was not there? So we would say that obviously the acceleration would be higher. Do you understand? Because moon is also there, so it's also pulling it. So greater the pull, the greater the acceleration. Though the value will be very small compared to um, what Earth is pulling, but still there will be an increase in acceleration. Do you understand?
Yes, sir.
Okay.
There
Any
is an
question?
additional force that will be pulling it, so therefore the acceleration will increase. That's what you're trying to say.
Exactly. Exactly. Suman, Ahmed, do you understand? Fahar, Anusha, Munib.
Yes, sir.
All right. Very nice. Now, this question, the next one, all right, this question I'm going to give you as homework because this is very simple. Um, it should be like, even if you don't do this, it's fine, but try to do this. This is, I'm very sure that now you understand the gravitational potential graph. You can obviously, do this easily. Anyway, then going to the gravitational potential change. Now, again, the same definition, work done per unit time, per unit mass. Oh my God, where's my, okay, work done per unit mass in moving this mass from infinity to the point. So that's what you're gonna write. And then it says a stone of mass m has a gravitational potential energy EP at the point X. Okay. And it then says that you got a and okay, the magnitude of gravitational potential at x is phi. State the relationship between EP and this. Now it's pretty easy. Like I told you, obviously, because it is work done per unit mass, so the EP will be equal to gravitational potential times mass. Is that clear, everyone?
Yes, sir. Sir, also I noticed in the definition that I think you mentioned we have to also specify writing it within the field.
Okay. Sorry.
Like in the definition, I think you mentioned that we have to write within the field so to carry one
Yeah.
more mark.
Yeah, yeah. No, that doesn't have mark. There's additional thing that you can write. That's correct. That's fine. Okay. One thing I just want to tell you, if it's not giving you like in here, I just want to make a point here. Please write that this would not be actually very correct. The reason is that right now it's talking about the gravitational potential, the magnitude of gravitational potential is phi. Now, because I wrote why I put it like I said, it is incorrect because the thing is that the gravitational potential has to be negative unless you're finding the change in it. So the gravitational potential has to be minus this. Do you guys understand that this would be correct statement? Understood? Please write it down, highlight it, because when in the last question it's talking about with reference to infinity, this time it's talking about just that point. So we have to put a negative sign. Do you guys understand this? Any questions, please?
Why? Can you explain again why negative? Like I didn't understand.
Gravitational potential at any point within the field is negative. Okay. Now,
Yes.
again, if you're taking, like, if you're comparing potential at infinity and it's moving from infinity to a certain point, then obviously this is zero, this is negative value, negative x. So you do minus x, it becomes positive, right? Because the change is like this. Do you understand? But in this question, the thing is that they're only talking about the magnitude of gravitational potential at x only. They're not talking about the reference of infinity. So we have to put a negative sign here. Do you understand? Because the gravitational potential at every point within the field is negative. Understood? That's why I put it wrong.
Yes, sir. I understand.
So these are very simple things that may affect your grade. So I'm just putting tips here. I don't want to I don't like solving questions myself, but it's important for you people. Now, an isolated spherical planet of R may be assumed to have all the mass concentrated at center. The gravitational potential of the surface is this. See, they've given a negative value right here. The stone of 1.3 kg is traveling from towards planet, so the distance of center changes from 6r to 5r. Do you guys understand this? Okay. Now it says calculate the change in gravitational potential energy of the stone. Fine. What exactly we are looking at is that actually, if you see that this means that the gravitational potential at the surface of the planet is minus 6.30 times 10 raised to power 7. Okay. Now, if I want to find the gravitational potential at a distance of 6r, then it will be 6 times less. How do I know this? Because gravitational potential is given by gm over r. Now, and minus sign. So if I want to put like 6r, what do you say? So I have to divide it by 6 because now I have to go 6 times ahead, which means now the gravitational potential at 6r is going to be minus, like I put it there, so it's going to be 6.30 times 10 raised to 7 divided by 6, like this. Do you guys understand this?
Yes, sir.
Okay. So this will be somewhat like 6.3 times 10 raised to power 7 and divided by, oh my God, divided by 6. So it is 1.05 times 10 raised to power 1, 2, 3, 4, 5, 6, 7. 1.05 times 10 raised to power 7 joules per kg. And then I have to find at 5r. So potential at this would be 6 point. So 5 times away would be divided by 5. So I can write it as, let's divide by 5. 1.26 times 10 raised to power 5, 6, 7. Okay. Now, so again, I just want to make a statement. Let's think a bit. 1.26 times 10 raised to 7 joules per kg. Now remember this. The gravitational potential, the potential or gravitational potential, let me just write it. Let's write a note where you're solving this question. So gravitation potential or just potential energy, whatever you're looking at, is a scalar quantity. And whenever you're dealing with scalar quantities, I should just tell you that you always do, when you're finding the change in the scalar quantities, you always do larger minus smaller. in vector quantities, we do final minus initial, but in scalar quantities, we do larger minus. So if this was a vector, then for a vector quantity, we would always find change. So this is a very basic thing that you should be aware of. Change, it should always be like final minus initial. And for scalar, it should be larger minus smaller. Is it clear, everyone? Now, speaking of this then, what do I need? I need to find the change in potential times mass, and that would give me energy. So the change in potential will be larger 1.26 times 10 raised to 7 if you're using no sign, right? So minus 1.05 times 10 raised to 7. If you take minus sign here, then you can do just, final minus ratio, it's fine. Multiply by the mass is 1.30. Okay, but that's not too hard. Okay, and where is the,
So we don't need the sign.
sorry?
We don't need the sign.
Yeah, we don't need it because if you put the sign like minus, you can do like, Gatika, you can do minus, and then you can take minus 1.05 minus 1.26, sign will be removed. Or you could just do it like this. Okay, let me just write. You can also write it like 1.05 times 10 raised to 7 minus 1.26. It will automatically be cancelled. So it doesn't really matter. Okay,
Okay.
like that. Now, you do 1.26 times 10 raised to power. Oh my God. Why am I so bad using calculators? Minus 1.5 times 10 raised to power 7. And this multiplied by 1.3. So this is going to be 2. Oh, I'm hating this app. With 2.73 times 10 raised to power 1, 2, 3, 4, 5, 6 joules. All right, is that clear?
Yes, sir.
So now every question that is going to give you a change. So you need to follow these steps. Step 1, find potential at position 1, whatever it is. All right. So we did it for 6R, right? In this example. Step 2, find potential at position 2, which is 5R. And then step 3, find change in potential by doing larger minus smaller. And step 4, would be that to find work done, you have to do change in potential times the mass of object. All right, do you guys understand this? Like that. So these are the 4 steps. Every single question follows the same. All right, any questions now? Please let me know.
So we could also do 1 over R2 minus 1 over R1 multiplied by gravitational potential. Would
Yeah,
that work?
that's the same thing you're doing. You're finding, like, what she's saying is the last thing before I end the class, because I know you guys have like chemistry class and the chemistry teacher was very angry at me last time as well. So if you're doing change in potential, you can do Gm, like minus Gm over 6R minus Gm over 5R. That would also give you the same answer. Okay, you could do that. It's fine. All right. Okay, Kartika. Anything else?
No, sir.
Okay. So I'm going to see you people in the next class. Have a nice day. The recording will be posted.